to thank the organizers, especially Professor Kim, for his invitation. This is my first visit to Korea, and I think I like this campus very much. Very beautiful. It's a pity that I may have no enough time to travel around and have to go back quickly. So thank you. Yeah, this is a summary of our recent joint work with Professor Yi Hongdu from Australia and Xinfu Chen from Pittsburgh. And these two guys are, this one is a doctor of Professor Matano in Tokyo University, and this guy is a doctor of Professor Belastiki, who was in Tokyo University and now go back to France, and two of my students. I will say a few words about the background and to describe our problem, and then to give a fundamental convergence theorem and use this theorem to provide some results with the various different boundary conditions. So, 3 years ago, Yi Hongdu and Professor Lin, who is here, studied such a model, logistic equation, and the most important thing is the domain is a variable one, and on the left boundary, this is a fixed boundary, normal boundary condition, and the right boundary is a moving one, a moving boundary. It takes the zero value and then moves rightward. If we consider only positive solution, then by the Hopf lemma, the gradient is negative, so this part is positive. Now here mu is a positive parameter, so this h will move rightward monotonically. And they use such a model to describe the spreading as a model to describe the spreading of a biological or new chemical species. With this one represent the front. So, if someone want to know more about such a Stephen-like free boundary condition, please ask Professor Lin. Okay. Here is one of the main results. That is a dichotomy of the long-time asymptotic, long-term behavior of U. This equation, let's look at this equation itself. It has two stationary solutions, 0 and 1. So when t goes to infinity, U may converge to 1 or 0. In this case, h also goes to infinity, and in this case, h is limited by this by some constant, which is less than this number. More precisely, they found the existence of a parameter of mu star when mu is big. Indeed, when mu goes to infinity, this can be neglected. So you can regard it something like a Cauchy problem. When mu is big, so it's easy to spread. Then you may easy to grow up and so converge to y. This is called spreading in this talk. Otherwise, when mu is small, for example, mu tends to 0. It means the boundary does not move. In this case, mu goes to 0. An additional condition is that for this phenomena is that the initial domain is very narrow. less than this. Less than. So here's a picture. If the initial data is small, and also the size is small, and the domain is not big, then a solution starts at H may goes to 0. It is called vanishing. Otherwise, if the initial data is big, it may it may spread. So this vanishing phenomenon is a remarkable result. The reason is that in 1970s, Erickson Weinberg also studied this problem, but for Cauchy problem without this free boundary. They obtained, they gave such a hair trigger effect, which says that for this equation, if you start at initial data which is non-negative and non-trivial, so no matter the initial data how small, this Cauchy problem the solution of it will grow up, no matter this one how small. So they call it a hair trigger effect. But now, in there, with such, they introduced such a free boundary, and then, so some small initial data may vanish. Later, Yu Hongdu and Professor Martineau and Wang Kelly also studied this problem in higher dimension. 2 years ago, Professor Yamada from Waseda University and his student studied this problem with a Dirichlet boundary condition at 0. So, in this case, even F is the logistic type, Y will no longer be a steady state because you have such a boundary condition. Indeed, in this case, instead of Y, such a positive solution will be a steady state for this problem. That result is the following. For monostable F and bistable F, they give some sufficient conditions for spreading and vanishing. It means under some condition, you converge to this guy or converge to vanish, converge to 0. So our problem is this boundary condition, a Laubin boundary condition. So here B can be 0. It means Dirichlet Y, and infinity corresponds to a Neumann Y. And for simplicity, we write we choose the initial data like this. Phi is some given a non-negative function, and the sigma is a parameter. And we only consider bistable nonlinearity in this talk because monostable and combustion type of nonlinearity and some are simpler than this bistable case. Okay, a bistable nonlinearity means that it has 3 zeros, 0 alpha and 1, and the integral between over 1 to theta is 0. And also we use this one to denote the potential. Okay, our question is how the long-term behavior depends on the boundary condition. The basic, before we state our results, let's first show a few basic results. The local existence of this problem and the global existence both are can be proved by standard argument. And so because the initial data is non-negative, and as I said just now, this by hope of lemma, this guy is negative, so this is positive, and H prime is positive, and also it can be shown it is bounded. So it converges to some limit. It may be finite or infinite. Our first result is a convergent result. Indeed, this theorem holds for general f, not only bistable f. Okay, the only condition is Cy and 0 is a steady state, trivial solution. So let this pair be a bounded time global solution. Bounded means U is bounded. U is bounded. H may goes to infinity. Okay. Then we have such a trichotomy, a dichotomy. A limiting domain may be limited, bounded interval, and in this case, U goes to 0. It means U vanishes, or it spreads to the whole space. But this U, the limit of this U, now what we can see is the limit is a stationary solution, steady state, non-negative, indeed a positive steady state, of course, satisfy this boundary condition. And in my talk, I will use this picture a lot. This is the fifth plane of this equation. Okay, V prime here, and F is a bistable one, so you can drive a lot of trajectories. This green one corresponds to the ground state, right? And this blue one, indeed, is something like this. And also you have some black trajectories which correspond solution of this equation with compact support and some periodic solutions. So what does this boundary condition mean? On the fifth plane, it means this line. Okay? So when B is large, in other words, this boundary condition so when B is large, then it intersect with this green and this black and all of this type of all of the trajectories. If B is small, it stands up and it does not contact with this one and this one. So in some case, when B is large, you have okay. For this elliptic equation, when B is large, you have such solution and such solution and periodic solution, and also 0 and some solution with compact support, a lot of stationary solutions. Our results say that it converges, U converges to a stationary one, but only these three types. The periodic one cannot be a limit, and the solution with compact support is also a limit. So this is the general convergence result. So using this result, we consider various boundary conditions. Okay, the first one is our Neumann Y. So in this case, this line is v-axis. So you have this solution exactly 0, and this half trajectory corresponds to this half ground state and 0. You have so many stationary solutions. So the conclusion is the following. Under such a Neumann boundary condition, so we have a trichotomy result, that is U may converge to 0 or to Y or to this ground state. We use capital V to denote the ground state. Okay, this is ground state. You have three choices, a trichotomy. We call this vanishing. In this case, the limiting domain is bounded Y, and in these two cases, U spread to the whole space. Okay. We call this a transition case. The reason is the following: because for any given phi, recall that this phi is the initial data. Okay, we fix this phi for given this phi and consider the behavior of the U according to this sigma. There is a sigma star such that when sigma is small, U vanishes. Initial data. When sigma big, it spreads, and exactly on sigma star, transition happens in such a sense. In some sense, this V, capital V, is unstable. Okay. Another interesting thing is that this sigma star can be infinity. It means nothing spreads. Everything vanishes. So this happens in case the initial data. The initial data is defined on a very small domain, and so when sigma is large, when sigma star is infinity, and the sigma is, it means no matter how large the sigma is, no matter how high the initial data is, the solution start at this initial data vanishes. This happens indeed when F decreases very fast, sufficiently fast. Okay. The second one is the Dirichlet boundary condition. As Yamada and his students proved, U may go to this one and this one. In this case, we have one stationary solution like this, and 0 is another stationary solution. No other the ground state is no longer a stationary solution, and so solutions with complex support is also not the omega limit. So our result is also a trichotomy. It says that when sigma is big, U converges to this big Y, to this one. And when it is small, converges to 0. But we will show this set, the sigma, such that it goes to 0, and this norm is an open interval. And this set is also an interval. So this way we denote it by zero and y. So this is sigma y and sigma 0. There's something in between because both of them are open. So what happens for sigma in between? Our results say that u goes to this because, yeah, I forget one thing, sorry. In this general convergence result, the convergence is in this norm. So now you have only two stationary solutions. So you must converge to one of them in this norm. Then for those sigma in between sigma 0 and sigma 1, you cannot converge. Sigma cannot be in this domain. It has to be for those sigma. U sigma must converge to 0, but not in this topology, but in this topology. Indeed, this U will converge to this shifting ground state. There is a function yt which goes to infinity, and there is a ground state moving to rightward to infinity, and U converges to this guy. In local uniform topology, this one is also 0. This one also converges to 0. Okay, now let's go to the Lobin boundary condition. When B is large, you have such stationary solution. When B is small, you have also these two, only these two stationary solutions. Our first result says that under the Lobin boundary condition, we have a trichotomy result. So for any given initial data phi, consider the solution start from sigma phi. There is a sigma star. When sigma is big, spread happens. It means U goes to V star. It converges to this big positive steady state. And when it is small, vanishing happens. U goes to 0. And in the transition case, it converges to a shifted ground state. Whether this shift is finite or infinity depends on B and the initial data. So this shift may be finite or infinity. If it is a real number, this solution will converge to a steady state which satisfies this one. Okay. The second result says that when spreading happens, that is U converge to the big one, U will converge to this guy. But near the free boundary HT, it is indeed something like this. So this is V star, and near the front, it is like this. So we will give an estimate of HT. HT, the limit of so HT minus there is a C star. This one is bounded and has a limit. This C star is given by this semi-wave. We call it a semi-wave. This equation is the profile of a traveling wave, but it is defined on the half space. Also, at the end point 0, we require Q satisfy this one. So we want to find a solution for this ODE which has the shape like this. The reason we require this boundary condition at 0 is that we use this Q. If this Q exists, we use this function, then we will get a solution like this, move to rightward, like the traveling wave. So this C star is nothing but the traveling speed of this semi-wave, and this one is has a limit, and this one has a limit 1, and this U, as I draw here, this U, the black one is the shape of U, and it approaches V star on the left side and approach this guy. Indeed, this one on the right side. Okay. Next, we consider the transition. When transition happens, I just said that this shift may be finite or infinite. Indeed, complicated. Just forget. I draw a picture here. Though we require that F is bistable, but the trajectory of the ground state is still complicated, can be still complicated like this. The trajectory like this. So there are two critical values here. We call it V. This one, okay. This result indeed see that when B is small enough and such that this line is located here, then y goes to infinity. That is, U converges to V minus x y t. This guy moves to infinity. If B is big, such in this region, then y converges to a constant. In this area, y converges to infinity or finite number depends on the initial data. So finally, we want to know how fast when y goes to infinity. So you know, this is a single equation. You cannot expect to a traveling pulse as a solution, but now we do have a such a shape move to rightward. So what's the speed? Our conclusion is this one. This, when y goes to infinity, indeed y equals to log t, and with such an error. So this number depends on lambda. Lambda is this guy, and B and capital A. Capital A is also defined by a small f. Okay. I may say a few words on the proof, but before that, I want to compare our results with the Cauchy problem. Yeah, let's go back to this equation again, but this time we consider Cauchy problem with Neumann boundary condition on the half line. So what we have known is that for this initial data, you have a trichotomy. For large initial data, you goes to 1, and for the small y it goes to 0, and for in the critical value it converges to the ground state. This is proved by them in 1999. But in their proof, they just show that there's a big sigma up star such that spreading happens, and a sigma small star such that vanishing happens. There's an interval in between. This is an interval. To show the sharpness, the unique of this interval is not so easy. So anyway, we solved it. And in Neumann boundary condition. In Neumann boundary condition, indeed, in 2005, Delatos and 3 years ago, Du and Professor Martineau gave such a result for this Neumann boundary condition problem. Okay. Also for Cauchy problem on the half line, but with the Dirichlet boundary condition, you can also have such trichotomy result. As I just said, they give such a trichotomy, but with with the transition case happen in an interval. Recently, with Xinfu Chen and other people, we prove this uniqueness, and also give the speed when it moves to infinity. Okay, I don't want to say more too much about the proof. Okay, for the general convergence result, we use zero number property first proposed by Engenant and later and by Martineau. So this is based on maximum principle. So our study, our approach depends on the maximum principle. And for this trichotomy results for Neumann boundary condition, we use this argument just as I said here. And okay, whether this y goes to infinity or finite number at the now we can prove it simply by a comparison principle and by zero number property. And to prove that when spreading happens, to prove U converges to such a shape, you just need to construct upper and lower solutions. But it's very complicated, so many parameters. And finally, to prove this propagating speed when y goes to infinity, you just use a manifold like this, but now you have a low-band boundary condition, so you should modify it a little bit. So we use such analysis along this center manifold. So in summary, in the low-band boundary condition, of course, including in some cases, including Neumann and the Dirichlet boundary conditions, first we have a trichotomy result. That is, U goes to a positive solution, a large positive solution. Or vanishes, it converges to 0. Or vanishing happens, that is, converges to a ground state, a finite shifted or infinitely shifted y. And so when spreading happens, the spreading speed of the front is indeed behavior like C star T. And in the transition case, y may converge to finite number when b is large, and to infinity when b is small. And when it goes to infinity, we have such an estimate. Yeah, it may go to infinity with such a speed. And so because we have a banquet at 6 o'clock, so I'd better to stop a little earlier. Thank you very much.